Okay, we're going to be talking about thermal conduction and the first law of thermodynamics today. Before we talk about the first law, let's talk about the zeroth law. It turns out there was this idea that people had in their heads when they did thermodynamics that seemed really obvious to them, so they used it, and they used it to do their calculations, and they came up with the first law and the second law, and then they sat back and said, wait a minute, there's this thing we've been assuming all along. We need to formally make that a law. It's more fundamental than the other two, so it better come first. And hence we have the zeroth law of thermodynamics. And it says that if two objects are independently in thermal equilibrium with a third, they are in equilibrium with each other. What does it mean for something to be in thermodynamic equilibrium? Well, if I place two objects next to each other, object A and object B, if A is hotter than B, if they're not in thermodynamic equilibrium, one of them, heat's going to flow from one of them into the other, all right? But if they are in thermodynamic equilibrium, that doesn't take place. No heat flows, all right? Now, the zeroth law says that if I have some object A, and it's in thermodynamic equilibrium with object C, in other words, I put them together and no heat flows between them. Now imagine, if you will, I have some other object B, which is also in equilibrium with C, which means if I put B and C together, no heat flows between them. If A is in equilibrium with C and B is equilibrium with C, that means that A and B are in equilibrium with each other. In other words, if I put A and B together, no heat will flow between them. All right? We use this quantity temperature to tell us whether things are in thermodynamic equilibrium. Basically, another way of saying the zeroth law of thermodynamics is, if two objects are in thermal equilibrium, that means they have the same temperature. And if two objects have the same temperature, that means they're in thermodynamic equilibrium. So if A and C are in thermodynamic equilibrium, no heat flows between them, they must be at the same temperature. If B and C, if I put them together and no heat flows between them, they must be at the same temperature, right? So that means the temperature of A is the same as C, the temperature of B is the same as C. That means that A and B are at the same temperature. And if two objects are at the same temperature, they're in thermodynamic equilibrium. So if I put A and B together, no heat will flow between them. If two objects are not in thermodynamic equilibrium, heat will flow from the one at the higher temperature, to the one at lower temperature. All right? From T hot to T cold. So in other words, thermodynamic equilibrium means that two objects are at the same temperature. If they are at the same temperature, you put them together, no heat will flow from one to the other. Now it turns out there's multiple ways that heat can flow through things. All right? One way is through conduction. I have something at a higher temperature, something at a lower temperature, and I physically connect them together. All right? Microscopically, what happens is, if we look in here, all right, here's this bar right here. It's hotter on this side, colder on this side. If we just take some arbitrary surface here, the stuff on this side of the surface will be wiggling more vigorously than the stuff on this side of that surface, and so this stuff is going to bump into that stuff, and on average, energy is going to be transferred and heat flows. All right? The energy moves, but the matter doesn't. It moves microscopically, but it's not like I'm physically taking stuff from over here to over here. All right? It's the energy that flows. All right? It's not like a wave, though, because it's uncorrelated random energy. The equation that will tell you the power that flows through a rod in steady state is this. We'll talk more about this in a minute, all right? We're going to get more quantitative in a minute with conduction. But first I want to show you two other ways that heat can flow. All right? Another way is convection. Imagine I have some hot air. The sun heats up the earth, all right, the surface of the earth, and the air close to the surface of the earth. Then heat conducts from the ground to the air. That means the air near the surface is hotter than the air up higher. What does hot air do? It rises, it goes, and it mixes with the air, all right? So once again, I've got something colder than something else, something hotter, something colder. Heat flows from higher temperature to lower temperature. One way it can do it is by physically taking the mass of the hot stuff and mixing it in with the mass of the cold stuff, bringing some of the cold stuff down and mixing it in with the mass of the hot stuff. So we're just spreading mass around. So heat moves because the hot stuff moves. All right? And that's what convection is. Convection can oftentimes be much more efficient at moving heat than conduction. All right? But convection doesn't happen in solids. It happens in gases and in liquids. Convection is fluid dynamics, and I believe I told you before that fluid dynamics can be very hard. So be aware that convection exists. It's important, but we're not actually going to we're not going to work problems with convection in this course. You'll have to go to a more advanced thermodynamics class to get that. Another way that energy can move to drive things towards thermodynamic equilibrium is radiation. All right? We call it blackbody radiation. And basically what blackbody radiation is if you look at any piece of material that's not at absolute zero temperature, the stuff inside of it is wiggling around microscopically, right? Well, what are you made of? What is the computer in front of you made of? What is the air in the room around you made of? It's made up of atoms, which are made up of protons, neutrons, and electrons. Electrons are charged. Protons are charged. So I've got these wiggling charged particles. And what do charged particles do when they wiggle? Well, when you study electromagnetism, you'll find out that wiggling charged particles radiate electromagnetic waves. All right? So blackbody radiation is electromagnetic waves being emitted by stuff wiggling. All right? And the waves that come out can be at a wide range of frequencies. You can have radio waves, infrared light, visible light, and so forth. The reason the sun emits lots of visible light is because it's very hot. And the hotter things are, the more shorter wavelengths of radiation they tend to produce. So the sun produces lots of visible light. You are not at absolute zero. If you turn off the lights, you appear to be dark, right? But that's just because most of the blackbody radiation that you emit is at longer wavelengths than what we can see. But if you get a camera that can see infrared light, you'll be able to use that camera to see that you actually do glow in the dark. And the basic idea with blackbody radiation is if I have something at a higher temperature and some object at a colder temperature, a lower temperature, they both are emitting this blackbody radiation, but the thing at the higher temperature is going to emit more blackbody radiation so that there's a net heat flow as this light goes from here and gets absorbed over here. There's a net heat flow that drives energy from the thing at higher temperature to lower temperature until equilibrium is reached. All right? Why is the Earth warmed by the sun? Because the sun is at a higher temperature, so it's emitting lots of radiation. Now, eventually, you would expect us to come into equilibrium with the sun. All right? But the problem is the Earth is also emitting, and well, we've got the hot sun over here. We've got cold, empty space over here. So we're emitting out into here, into empty space, and only a small part of our emissions are going back to the sun. All right? And so until the whole universe comes to the same temperature, we're not going to come into equilibrium with the sun. But there will be this constant flow of heat from the sun to the Earth because the sun is at a higher temperature. Now, it turns out the rate at which things emit blackbody radiation is not hard to calculate. It's a very simple equation, but for lack of time, we're not really going to work problems with blackbody radiation in this class. All right, so let's go back to thermal conduction, the one we are going to do problems on, and let's talk about it more carefully. I said that the equation that described the power flowing through a rod is Ka over L Th minus Tc. What does this all mean? All right, we're not going to derive this equation. It turns out from first principles calculating how things conduct can be very hard. But once again, just like with thermal expansion, we're going to stuff all of the hard physics into this constant right here and then show that all this other stuff needs to be exactly what it is. All right, so this constant here, K, is called the thermal conductivity. It's a property of the material that the heat is flowing through. So you have an iron bar, you would look this up online, find the thermal conductivity of iron and so forth. All right? Now, this equation is valid only when your system is in steady state. It's not an equilibrium, right? Thermal equilibrium means the temperature is the same everywhere. So heat is flowing, it's not an equilibrium, but it's in steady state. What does steady state mean? Well, here's kind of an analogy here. Imagine I've got a mountain, and there's a lake up on this mountain, and there's a river that flows out of that lake down to the ocean. All right? Now, constantly this lake is being filled by other rivers and things coming into it, rain runoff and whatnot. All right? And then this water flows down to the ocean. Equilibrium would be all of the water at the same height. No more water flowing. All right? But water is flowing. It's flowing from a high potential down to a low potential. All right? But imagine that this lake and the ocean are always at a constant level. This lake is always being replenished and water is always being taken out of the ocean so that they stay at a constant level. What that means then is that water is going to flow down this river, but it's always going to flow at a constant rate, all right? If I take any little piece of the river, there's water flowing into it and water flowing out of it. They're flowing at the same rate. So if I look at some piece of the river, the depth of the water is not changing with time. I'm not getting more water in that piece of the river because the rate of water flowing in and the rate of water flowing out are the same. That is what steady state is. So let's say I have an aluminum bar and I stick one end in boiling water and one end in ice water. So this is always at 100 degrees C and this end's always at 0 degrees C. All right? Imagine I do that suddenly. Initially this bar is at room temperature. Heat's going to flow, but this bar is going to start to heat up, right? This end's going to start to heat up, this end's going to start to cool down. That is not steady state. But if I wait for a long time, and I've always got boiling water here and always ice water here, this will never come into equilibrium because I'm holding the two ends at different temperatures. But if I wait a long time, eventually it'll settle down, such that if I measure the temperature here, or if I measure the temperature here, there are going to be different temperatures, but if I look at any point, that temperature is not changing in time. I'm not building up heat at that point. And if I take any cross-section or any little slice of my bar, the rate of heat flowing in will always equal the rate flowing out. And the rate of heat flowing is constant all the way across the bar. All right? That's steady state. When I'm in steady state, this equation holds. All right? And this equation tells me the power, the heat that's flowing through the rod. If I take any surface, that's the heat flowing through that surface, and it's the same everywhere on the rod because I'm in steady state. All right? So the power flowing through my rod is equal to this. It's proportional to something called the thermal conductivity. A is the cross-sectional area of my bar, right? There's A right there. L is the length of my bar. And then this right here is the difference in temperatures of the two ends of my bar. All right? Okay, why would this equation depend on the area? Why would it be proportional to the area, to the first power? Very simple argument. Imagine I have two bars that have the same cross-section, all right? And I hold them between these two temperatures. Identical situation. I'm going to have the same power flowing through each of them. Now imagine I put them together to make one big bar. Now I'm going to have twice the power flowing through, right? So two bars, I put them together, I get twice the area, I get twice the power flowing through. So it makes sense that it ought to be proportional to the area, all right? Now imagine, if you will, I have a really long bar, but let's imagine that that bar is made up of, let's kind of imagine it being broken into two pieces, all right? So I have temperature hot here, I have temperature cold here, all right? What's the temperature right here? Halfway in between. Well, let's think about this. We're in steady state. That means the power flowing here is the same as the power flowing here, as flowing here, as flowing here. So that means I have the same power flowing through the two rods, all right? These two rods have the same length, the same area. They're exactly the same situation, right? And so therefore, to have the same power flowing through them, I need to have the same temperatures across them. To have the same temperatures across them, that means this temperature must be halfway in between, all right? Okay, so I look at this and I say, well, in order to, if I double the length to get the same power flowing through, I have to double the temperature going across them. So it makes sense that my equation ought to depend on the difference in temperature divided by the length. Why difference in temperature divided by length to the first power and not to the second or the third power? Well, I can't think of a really quick hand-waving argument, so I'm going to dodge that question right now and just say it should depend on the change in temperature over the length. All right? What happens if I have thermal conductors in parallel? Imagine that I say to you, I have a copper bar, and I have an iron bar, and I have some temperature T hot over here, some temperature T cold over here, and I ask you for the total power flowing from T hot to T cold. Well, you just treat them independently. They don't interact with each other. I have some power copper flowing through here, and some power iron flowing through here. The total power is just going to be the sum of the two. All right, so when they're in parallel, it's really easy to calculate how much power flows. You just treat each one of them independently. A more difficult problem is, what if I said I have let's say, a copper bar here and an iron bar here, and I have some temperature T hot, some temperature T cold, what's the power flowing through? How would you solve that? All right? Well, here's the deal. We know that the power flowing through the copper is the same as the power flowing through the iron. There's just one power. All right? So the way we would work a problem like this is we would say, well, let's just call this T middle. All right? And let's pretend like we know what T middle is. We don't. But let's just work the problem as if we did. I could find the power flowing through the copper just by saying the power flowing through the copper is just the thermal conductivity of copper times the cross-section of my bar divided by the length of my copper bar times the temperature difference, T hot minus T middle, right? And then I could calculate the power flowing through the iron bar, and that's just the thermal conductivity of iron, the cross-sectional area, the length of my iron bar, and then the temperature. This is going to be hotter than that, right? Because heat's flowing this way, so the temperature difference is going to be T middle minus T cold, right? Then what I do is I say, well, look, if I'm in steady state, the power flowing out of the copper is the same as the power flowing into the iron, so these two are the same power, all right? So now, if you kind of ignore this, and let's just call it power, right? Power is equal to this, power is equal to this. I have two equations, two unknowns. I don't know power, I don't know T middle, all right? So now it's just two equations, two unknowns, and you can solve and find what the power is and what the temperature is at the junction between the copper and the iron rod. What if I have a non-uniform area? What if I have a rod that's not a constant cross-sectional area? What if I have something where the material is, so let's say I have a bar like this, and this part down here is iron, this part up here is copper, but they're not like, they're kind of weird, wiggly like that. What about more complicated things? Well, it turns out you need a more complicated differential calculus version of this equation here, all right? And you will get that if you do Physics 318. But for this class, we're going to stick with simple stuff. Just know it can be done, but we're going to stick with simpler things for this course. All right, so that is our end of discussion on thermal conduction. Now we're going to discuss the first law of thermodynamics. The first law of thermodynamics is basically conservation of energy applied to thermodynamics. It basically says, imagine I've got some gas, all right? I can do different things to that gas, all right? I can squish it, right? I can squish it. I can push on it and make the container smaller. When I do that, I'm doing work on the gas, right? I'm pushing on it, and it'll change the energy of the gas, all right? I can do work on it. I can let heat flow into it, right? That will change its energy. So the first law of thermodynamics says, I've got this thing, this thermal internal energy. The internal energy. The first law of thermodynamics basically just says the change in internal energy is equal to the work I do on the gas plus the heat that flows into the gas. Simple conservation of energy. I've got some thermal internal energy. I can change it by doing work on the gas. I can change it by having heat flow into the gas. And that's basically the first law of thermodynamics right there. Just conservation of energy. Now, conventions. You can do work on the gas. When you're doing positive work on the gas is doing negative work on you. When the gas is doing positive work on you, you're doing negative work on the gas. By convention, W will be the work done on the gas, not the work done by the gas. So if W is positive, that means work is putting energy into the gas. Until we talk about heat engines, where we'll make a brief exception, Q will always refer to heat flowing into the gas, right? So heat can flow in or out. Positive Q means heat's flowing from the outside into the gas, all right? So work plus Q is how much the internal energy of the gas changes, all right? Okay, that's the first law of thermodynamics. So what is the work done on a gas? Well, work is force times distance, right? A little bit of work, an infinitesimal amount of work is force times a little bit of change in distance, right? Why am I writing dx and dy work? Well, maybe the force changes as x changes, right? Like if I'm pushing on a spring, for example, all right? The force is a function of position, but I can find the work done just by integrating this. Integrate d work from having no work done to all the work done. That gives me work. Well, that's just the integral, right? I integrate both sides of f dx. If I'm integrating work from no work done to all the work done, I'm going to integrate from where I started to where I ended. All right? So that's how I find work. It's force times distance. Well, let's look at a gas. So imagine I have a gas and I have a little piston here. All right? And I'm pushing down on the piston to do work on the gas. All right? A little bit of work is, well, what's the force? What's the force that the piston is pushing down on the gas with? Well, the gas is pushing up with a force of pressure times area, right? So that means equal and opposite forces, right? The piston is pushing down on the gas with a force of pressure times area, right? So pressure times area times dx ought to be the work, all right? We integrate the two of them. Well, I'm going to integrate from 0 to all of the work done, all right? And I'm going to integrate from where I start to where I end. Well, now notice something. dx, I move x a little bit. Here's dx, all right? Multiply that by area, and I get this little piece of volume, all right? So area times dx is that little piece of volume, all right? But instead of defining dV to be that little piece of volume, I'm going to define dV to be how much the total volume of the gas changed. The gas's volume went down by that little piece right there. So I'm going to define, if I define dV, let's call this thing here, let's call it smiley face, all right? Smiley face is that little bit of area right there. Smiley face is equal to area times dx, right? But if smiley face is positive, the gas has gotten smaller, so I'm going to define that to be negative dV, all right? So V is the volume of the gas. When the gas gets smaller, positive work is done, right? I have to push down and compress the gas. That's positive work being done on the gas. So my integral will look like this. Integral P negative P dV from my initial volume to my final volume. So there it is. I integrate this. The work done on a gas is just minus the integral of P dV from volume initial to volume final. All right? Maybe call that I for initial. All right, so that's the work done on a gas. Groovy? Okay. Now, notice, it's work done on the gas, not just work, right? It's positive work if it's done on the gas. Negative work is being done on the piston when positive work is being done on the gas. If the piston is expanding, if the gas is pushing the piston and doing positive work on the piston, negative work is being done on the gas. If the volume is increasing, negative work is being done. If the volume is decreasing, positive work is being done, increasing the energy of the gas. All right? Now, as you recall, back from calculus, when I took calculus, I was always like, okay, we do an integral, and the integral of f of x dx is just the area under the curve, right? From x equals this to x equals that. And I wondered over and over again, why did we want to know the area of the curve under a curve so badly that we had to take 2 semesters of calculus to learn how to do areas under a curve? And then I took Physics 220, and we learned that no, an integral is actually just like a sum. It's a sum of all of these little infinitesimal things. D smiley is equal to smiley, right? But I'm adding up a whole bunch of infinitesimal things to see what it gets to. It's like a special sum, all right? But in addition to being a special sum, it does turn out to be the area under a curve. So if work is the integral of minus P dV, all right, from V initial to V final, what that means is if I plot pressure as a function of volume as I do something, the work that's done on the gas is just going to be the area under that curve. Well, negative the area under that curve, all right? If I integrate this way, all right, that's an increasing volume. I'm going to get negative work. If I integrate this way, right, if I flip the integration limits around, I get a minus sign. So if I integrate this way, that's positive work. The volume is going down. I get a net positive work on the gas. All right? So we can use what is called a PV diagram to help us see the work done as we do a process on a gas. Now notice, when I draw my PV diagram, right, PV, and imagine my gas goes from here to here, some things are what we call state-dependent variables and some are path-dependent, right? If I am right here, right, the pressure and the volume and the temperature. If I know how many moles of gas I've got, and I know where I am on my PV diagram, that tells me all of these things. Temperature is a state-dependent variable. It doesn't matter how I got from here to here, right? If I go from here to here along this path or this path, the temperature change will be the same. It only matters where I started and where I ended, right? So temperature is what we call a state-dependent variable. The work done, however, if I go from here to here, all right, it's the area under the curve, right? Compare the area under this curve to the area under this curve, all right? Increasing volume, the work will be negative, but for this path, it'll be a smaller negative amount of work, whereas for this path, it will be a greater negative amount of work. So work is a path-dependent, right? Temperature was state-dependent, but work is a path-dependent parameter. It depends on not just where you start and end, but how you traveled the space in between. All right? Kind of like, yeah, anyway. So let's look at some common processes that you can do with a gas. An isobaric means constant pressure. So the change in pressure is 0. Isobaric. So in a PV diagram, that means the pressure is constant. All right? PV, pressure is constant. All right, so if I look here, what's the work going to be done? The work is just going to be the integral of negative P dV from V initial to V final, right? But pressure is constant, so it comes out of the integral minus pressure dV, and the integral of dV is just then going to be the change in volume. So work for a constant pressure process is just minus P dV, all right? The pressure is constant. If we look at PV equals nRT, the ideal gas law, that tells me then if the pressure is constant, all right, the volume is going to increase in proportion to the temperature. All right, so how do I have an isobaric process? Imagine I have a balloon, right? And we discussed earlier that if the pressure inside a balloon weren't really, really close to atmospheric pressure, the balloon would pop, right? Because the rubber's not very strong. So if I put a balloon up next to a heater and I let heat go in, all right, as it expands, the gas will stay at a constant pressure, all right? So the work done will just be minus P delta V because it's an isobaric process, and the volume will be proportional to the temperature of the air inside the balloon, all right? That's a constant pressure process. Another example is imagine I have a piston holding air. I've got this piston right here. I'm going to put some weight on it. Now if I put a flame under here and I heat it up, all right, the pressure will always be constant because the pressure is just enough to generate the force to hold this piston and the mass up, all right? So there's a constant temperature process. There's another example, or constant pressure process where I can change the temperature of the gas, the volume increases proportionally, and the work done is just minus P delta V. All right, so there's constant pressure, isobaric. Isovolumetric means the change in volume is 0. The volume doesn't change. So what would that look like on a PV diagram? All right, the volume doesn't change. Let's say I change the pressure. I go from here to here, but the volume doesn't change. All right, so PV is equal to nRT. If the volume doesn't change, that means the pressure is just proportional to the temperature. All right? What about the work done? Work is equal to minus integral P dV. If I integrate, so imagine I've got some curve, but I integrate from here to here. I don't change x, right? I'm integrating this curve right here is what I'm doing. Ignore that. That doesn't make sense. I'm integrating from here to here. What's the area under that curve? It's 0. I don't change the volume. Volume initial and volume final are the same. So the work done in an isovolumetric process is 0. No work is done if I don't change the volume of my gas. So if I have a piston and I lock the piston in place and heat it up, no work is done. All right? If I have a balloon and I deform it, but I keep the volume the same, no net work is done. All right? So the work doesn't, there's no work done on the balloon. What does that tell me about the change in internal energy? Change in internal energy is work plus Q, all right? Work goes to 0. So the change in internal energy is just Q. All right? It's just the heat that flows in. Let's go back to our isobaric, all right? For an isobaric, well, change in internal energy is work plus Q, all right? So it's going to have some work and it's going to have some Q. All right? Let's look at an isothermal process. Isothermal means the pressure doesn't change. PV is equal to nRT. So isothermal means the temperature doesn't change. If the temperature doesn't change, that means that the pressure is going to be nRT over V, right? It's going to go as 1 over V. So if I plot a PV diagram for isothermal, it's going to look like this. As the volume increases, the pressure goes down. So it's going to be some sort of a curve. And the limit is the volume goes to 0, the pressure goes to infinity. And the limit is the volume goes to infinity, the pressure goes to 0. All right? So that's what an isothermal process looks like. What is the work done on an isothermal process? Minus P dV, V initial to V final. All right? For an isobaric, the pressure came out and the integral was easy. For the isovolumetric, we didn't integrate over any change in volume and we got 0, and that was easy. Now both the pressure and the volume are changing. But I have an equation that tells me the pressure as a function of volume, so I can just plug that into my integral. And that's going to be nRT over V dV. All right? Well, nRT is constant for our isothermal process, so that just comes out, and I have negative nRT times the integral of V initial to V final dV over V. Well, if you remember, integrating 1 over x dx, that's just the natural logarithm, so this is just going to be the natural logarithm of V evaluated from V equals V initial to V final. Now, taking the logarithm of a volume is kind of screwy because volume has units, right? If I convert volume into different units, will my logarithm be different? It's kind of screwy. Logarithms don't like units, but that's okay because when I evaluate my limits, I'm going to have natural logarithm of V final minus natural logarithm of V initial, and I can just use my property of logarithms that says this is equal to the natural log V final over V initial. All right? Or I can note that taking a minus sign is the same thing as flipping that over, and I can write this as nRT natural log of V initial over V final. And you see here, natural log of 1 is 0, right? If I don't change the volume in an isothermal process, nothing changed, and no work is done. If my final volume is bigger than my initial volume, I'm taking the natural log of something less than 1, and I'll get a negative work. If my final volume is smaller than my initial volume, I'm going to get positive work. So if I'm compressing the gas, making the gas smaller, that's doing positive work on the gas. All right? So there's the work for an isothermal process. All right? Now it turns out that the internal energy in a gas is just proportional to the temperature. All right? So for an isothermal process, the change in internal energy is 0, which means that work plus Q is equal to 0, which means that Q is equal to minus work, but minus work is just nRT natural log V final over V initial. All right? So if you do an isothermal process, knowing the change in volume, you immediately know how much work is done, and you know how much heat went into the system as it was changed isothermally. How do you do an isothermal process? Take a piston full of air and compress it while that piston is in ice water, and do it slowly so that as this piston tries to heat up, heat flows out and it stays at 0 degrees C. All right. Okay, now we're going to talk about an adiabatic process. Now it turns out there's two different things we mean when we say adiabatic. Literally, adiabatic means no heat. So whenever I say adiabatic, you know that the heat that flows in this process is 0, which means the change in internal energy is then just going to be equal to the work done because there's no heat. All right? But there's two kinds of adiabatic. One is a reversible adiabatic process. All right? So the idea with a reversible adiabatic process is, here's my PV diagram. All right? I take my piston. So how do I do a reversible adiabatic process? I'm going to let the piston expand. All right, so there's some pressure, the piston expands. The volume increases, all right? Volume increases, but no heat is flowing in, all right? The piston is doing work, so negative work is being done on the piston, which means its internal energy is going down, right? PV equals nRT. The volume is increasing, all right, but the temperature is going down, right? Because negative work is being done, which means the change in internal energy is negative, and I told you that the change in internal energy is proportional to the temperature change. So as we expand, as the volume expands, the temperature goes down, which means the pressure is nRT over V. The temperature is going down, the volume is going up, the pressure is going down. So the pressure goes down. In fact, the pressure is going to go down faster than an isothermal process. Going the other way, I take my piston, I squish it down, all right? The volume goes down, but I'm doing positive work on it, which means the temperature must be going up, so the pressure goes up. So a reversible adiabatic process on our PV diagram looks kind of similar to an isothermal, but not quite the same, all right? It's kind of a more drastic change in pressure, because whereas with the isothermal, if I squish the gas, it tries to heat up, and then heat flows out in an isothermal. In an adiabatic, no heat flows, therefore the pressure goes up more because there's no heat flowing out to reduce the temperature. All right? So, in a reversible adiabatic process, we know that if I ever say adiabatic, Q is equal to 0, and the work then is just the change in internal energy, because Q is equal to 0. All right? There's another process that we also call adiabatic, which is an adiabatic free expansion. This is very different from our reversible adiabatic process. So in a reversible adiabatic process, I compress my piston, or I let my piston expand, but my piston is insulated, so no heat can flow in or out, all right? And I can draw that on a PV diagram. I can go backwards, back and forth. I can push it down. I can let it come up, whatever. A free expansion is an irreversible process. This is how you do a free expansion. You have a box, and it's got a partition in the middle, and you've got a whole bunch of gas on this side. Then you slide the partition out and let the gas expand to fill the whole box. All right? That's what we call a free expansion. And it's adiabatic because Q is equal to 0. No heat flows in or out, right? Our box, let's assume our box is insulated like before, and we're just pulling out the partition and letting the stuff expand, all right? And to fill this other space, all right? But it's a free expansion. So although Q is equal to 0, if Q is equal to 0, that tells us that the change in internal energy is equal to the work. But here, work is actually being done, right? If I compress the piston, I'm doing positive work on it, right? If I let the piston expand, right, I'm just doing integral of P dV. Work is minus integral P dV, right? And that's going to be something. The pressure, I've got a pressure, I've got a change in volume, I'm going to get some work, all right? How do I actually calculate how much work is done? We're going to come back to that later. Adiabatic's a little more complicated. But just know that work is done. In a free expansion, however, what happens? I've got this, so let's think microscopically here for my adiabatic process. So my reversible adiabatic process, I've got this piston. And imagine the piston's coming down. I've got this little particle, it bounces off of the piston. It's going to come out with more energy because it's being hit by a moving piston, right? My piston is like a bat. Okay, maybe it's not moving as fast as a bat, but it's the same idea. My ball comes in, the bat is moving, it comes out with more energy. So the internal energy of my gas is changing as the piston compresses. Or as the piston expands, it'll come off with less energy than it went in with. So the internal energy changes as I do a reversible adiabatic compression or expansion. But in a free expansion, what I've got is I've got this wall here. Here's my bat, and here comes my ball. My ball's about to hit the bat, and then suddenly the bat isn't there, and my ball just keeps moving. All right? So the velocity of my ball doesn't change. The energy of my ball doesn't change. So in a free expansion, no work is done, which means there's no change in energy. So for any adiabatic process, the change in internal energy is equal to the work. But for an adiabatic free expansion, the work done is 0, all right? Which means the change in internal energy is 0. How would I plot a free expansion on my PV diagram? All right? So I start at some volume, and then let's say my volume goes up by a factor of 2. No change in internal energy, all right? So PV equals nRT, and I told you before, the change in internal energy is proportional to the change in temperature. So in adiabatic free expansion, the temperature doesn't change. So if the volume goes up, the pressure must go down, all right? So maybe this is like an isothermal process, right, where we do something like this. No, that's not what happens. It's not like an isothermal process because it's irreversible. I just go from here, then I'm not in equilibrium. I can't even talk about pressure and volume. It's kind of some crazy thing. And then when we come back into equilibrium, we're down here. So there is, if this were an isothermal process with a line that connected the two, I could do the integral of that line and get work, and it wouldn't be zero. For free expansion, there is no line. You're here, then you're not in equilibrium, you're not in equilibrium, I can't do this, and then suddenly I come into equilibrium over here. So it's a really screwy, irreversible process. No work is done. We get from point A to point B on our PV diagram, but we do it without taking a real path on the PV diagram, and no work is done.